GP120, GP41, CDR4, CD4, CCR5. I don't understand any of this. I wish there was someone that could teach me about HIV in a fun and creative way.
Did somebody say HIV?
I sure did. Who are you?
I'm Dr. Black, the real Dr. Black, and this is my magic school bus.
Wow.
Get on board so we can learn all about HIV.
Okay, I have no problem with this. Where are we going, Dr. Black?
We're going to the human host.
Oh boy.
Well, here we are at the human host.
How are we gonna get in?
Well, there are many ways of getting inside of the human host. You can have protected sex, sharing a dirty needle, or having a blood transfusion, all with someone who is HIV positive. Let me just press this button on here and I'll transform this magic school bus into a dirty needle.
Wow. Whoa. Okay, Dr. Black, now that we're inside the human host, where are we headed to next?
Well, right now we're looking for a T helper cell, the host of the HIV variant. And would you look at that? There's one right now.
Wow. Look, here comes an HIV
It
variant.
looks like it's coming to infect that T helper cell. Let's go and see what happens. First, the HIV glycoprotein GP120 binds to the helper T cell's CD4 receptor, which exposes the CCR5 co-receptor. GP120 binds to the co-receptor, which causes GP120 to slip off, and the membranes are drawn closer, allowing GP41 to insert into the host membrane and form a hydrophobic channel, which forces water out and fuses the membranes, finally allowing the viral capsid to enter the cell.
Wow.
Quick, let's follow it in.
Okay. Are you okay? That sure was a rough entry.
Yeah, but look over there. Now that the viral capsid is inside the cell, the reverse transcriptase is about to get to work. Remember these 4 guiding rules for successful HIV genomic replication. Number 1. Double-stranded nucleic acids bind using complementary sequences and anti-parallel orientation. 2. Template swapping happens. 3. Growth only occurs at the 3' ends. And 4. RNA is actively removed from RNA-DNA hybrids by RNase H. The tRNA binds to the primer binding site near the 5' end, acting as a primer for reverse transcriptase so it can get to work synthesizing the minus strand in the 3' direction. The newly synthesized minus-sense DNA then template swaps to the 3' end of the RNA. Meanwhile, the positive-sense mRNA strand of the RNA-DNA hybrid is degraded by RNase H activity, while the RNase H-resistant polypurine tract remains intact, acting as the primer for positive-strand DNA synthesis, which synthesizes in the 3' to 5' direction. The final pieces of RNA are then degraded, and the positive strand DNA template swaps to the PBS prime sequence of the minus strand DNA. Strand displacement synthesis of the minus strand completes the entire minus strand DNA. The positive sense DNA then completes synthesis to create the full proviral DNA. Integrase degrades the 3' ends of the proviral DNA to give sticky ends with free hydroxyl groups. Host DNA is randomly cleaved and partially digested. The proviral DNA is integrated and the DNA strands are repaired to ensure its proteins and nucleic acids get expressed.
Now that the viral genome has been integrated, Dr. Black, what happens next?
Well, now we have to wait for the CD4 T cell count to get below a certain threshold. Then we can start observing expression of the viral genome.
Wow, how long does that take?
About 3 to 4 years.
Oh man, I keep trying to process these transcripts, but I just keep slipping. This one's not long enough to make any proteins. Okay, here we go again. Oh, this one's perfect. I can make some tat with this. Better send it to the ribosome. Thanks, Tat Cat. Now I can make like I can transcribe a full transcript. Wow, more tat. Now I can definitely not slip off and probably make the full transcript. Wow, even more tat. Now I can really make a whole genomic RNA. Wow, so much tat. I definitely won't slip off the DNA and I'll be able to transcribe a whole genomic RNA now.
Hey, Dr. Black, what are some different ways of regulating expression of this viral genome? That's a great question and a great segue to the next part of our journey, which will go over the different modes of HIV regulation.
Hi, I'm a spliceosome. I'm gonna alternately splice these mRNAs so that I can make a variety of proteins from one type of mRNA. Look at this beautiful mRNA transcript. I'm gonna send this right to the ribosome to make a bunch of different types of proteins. Look at these copies of the same mRNA. There's 3 copies. I wonder what I'm gonna do to make these into different proteins. Oh, I know. I'll use open reading frame number 1. Wow. Now I can read this and translate it into a first set of proteins. Better send it to the ribosome. Now I'm going to use open reading frame number 2. Awesome. Open reading frame number 2. Now I can make a second set of proteins from the same exact mRNA. Better send that one to the ribosome. Now for open reading frame number 3. Wow, the same exact mRNA, but now I can read it differently. Better translate into a third set of proteins. Off to the ribosome with you scurvy dog.
Hi, I'm Revan Expo. I'm here to export my gRNA to the plasma membrane, where it will be assembled by the capsid in the capsid. I'm Revan Expo. I've got a package for you.
Oh, okay, cool. Genomic RNA, nice. Now that I have my genomic RNA, I'm ready to put on my capsid proteins. Okay, see you later guys. I'm about to butt out of the plasma membrane.
Gee willikers, Dr. Black. This was sure entertaining and educational. Yep, now it's time to head back to the magic school bus so we can have some sort of coherent story to this movie.